Now we have a complete way to evaluate the enthalpy of any compound at any state T and P. Equation 13.9. H Tp is equal to H naught F plus H in bracket H Tp minus H T reference P reference, close bracket. In words, the total enthalpy equals the enthalpy of formation plus the sensible enthalpy change from the reference state to the actual state. Let's look at each term. Term 1, H naught F, accounts for how the molecule was created from its elements. Always the same for a given compound. Look it up from table A to 5. Term 2, the sensible enthalpy change accounts for how much the temperature and pressure differ from the reference state. This is a difference at fixed composition. So it can be taken from steam tables or ideal gas tables, table A to 3, because the terms cancel in differences. Some key values from table A25 that you will use constantly: CO2, H naught F is equal to negative 393,520 kilojoule per kilomole, H2O in gram, H naught F is equal to negative 241,826 kilojoule per kilomole, H2O in liters, H naught F is equal to negative 285,830 kilojoule per kilomole. Well, O2 and 2CH2, the H naught F is equal to 0 since they are the datum elements. Notice that H2O liquid has a more negative H naught F than H2O gas. The difference, about 44,000 kilojoule per kilomole, is the latent heat of condensation. We'll use this when distinguishing between higher and lower heating values. Let's apply this for a real example. This is a classic textbook problem statement. Pulverized coal, modeled as pure carbon, enters a combustor at 298 Kelvin, 1 atm. Oxygen enters at 400 Kelvin, 1 atm. Carbon dioxide exits at 500 Kelvin, 1 atm. At steady state, find the rate of heat transfer per kilomole of coal. So the reaction C react with oxygen gas will form CO2 gas. Step 1. Energy rate balance at steady state. Q dot N dot is equal to HCO2, which is 500 Kelvin, minus HC 298 Kelvin minus HO2 400 Kelvin. I'm neglecting kinetic and potential energy effects, and there's no sharp work. Step number 2. Evaluate each enthalpy using equation 13.9. For carbon, entering at 298 Kelvin, which is the standard state, Hc, which will equal to 0 plus 0, 0 kilojoule per kilomole. Carbon is the datum element and it's exactly at the reference state. Both terms are 0. For oxygen entering at 400 Kelvin, HO2, not to be confused with water, is equal to 0 plus H 400 Kelvin minus H at 298 Kelvin. From table A23 for O2, H at 400 Kelvin is equal to 11,711 kilojoule per kilomole. H at 298 Kelvin is equal to 682 kilojoule per kilomole. Therefore, the H for O2 is equal to 0 plus 11,711 minus at 682 equal to 3029 kilojoule per kilomole. For CO2, exiting at 500 Kelvin, H of the CO2 is equal to negative 393,520 plus H at 500 Kelvin minus H at 298 Kelvin. From table A23 for CO2, H 500 Kelvin is equal to 17,678 kilojoule per kilomole. H at 298 Kelvin is equal to 9,364 kilojoule per kilomole. Therefore, the H of CO2 is equal to negative 393,520 plus 17,678 minus 9,364 equal to negative 3 at 5206 kilojoule per kilomole. And step 3, our final answer, Q dot over n dot is equal to negative 3 at 5206 minus 0 minus 3029, which equal to negative 3 at 8235 kilojoule per kilomole. The negative sign means that heat is transferred out of the control volume, which makes sense because combustion is exothermic. This is the general procedure for any combustion energy balance. You'll repeat this pattern on every problem from here to the exam.